This is lesson 4-6 from the Algebra Readiness textbook. For today's lesson, we are going to learn to classify and compute with rational numbers. Biologists classify animals based on shared characteristics. The cardinal is an animal, a vertebrate, a bird, and a passerine. Just like scientists classify animals, mathematicians classify numbers. Instead of vertebrates and invertebrates, mathematicians have rational and irrational numbers. In the same way that these scientists are classifying animals based on one criteria, either they have a backbone or they don't, mathematicians classify numbers based on one criteria, if they have a fraction form or if they don't. In your notes, please write down the definition of rational number. A rational number has a fraction form. An irrational number doesn't have a fraction form because non-terminating and non-repeating decimals cannot be written as fractions. Most numbers that you can think of fall into the rational category. A rational number, again, is one that can be written as a fraction. So any fraction you can think of is a rational number. So as an example, all fractions, positive and negative. Let's say 2/3, 1/8, 17/43, any fraction at all. You've also learned that most decimals can be written as a fraction. For example, terminating decimals. Terminating means that it ends. If you're terminated from a job, that means your job ends. So terminating decimals. For example, if I gave you the decimal 4/10, you could write this as a fraction, 4/10. If you can convert something to be a fraction form, then that number is rational. Whole numbers are also rational. Let me give you an example. We all know that the number 7 is a whole number. 7 can be written in fraction form as 7/1. In fact, repeating decimals can also be written as a fraction form. Repeating decimals like 3/10 repeating is the same as 1/3. It has a fraction form. So at this point, you must be thinking, all right, so then what would possibly be irrational? Well, the only way to have an irrational number is if it's a non-terminating and non-repeating decimal both at the same time. Let me give you an example. Pi is irrational. Pi is written as 3.141592, and it goes on forever and ever and ever, and it does not repeat. It's an irrational number. Another way to make an irrational number is the square root of a non-perfect square. What does that mean? Well, we'll get into that a little bit more, but the square root of 16 means what number times itself equals 16? Well, that's 4. And we know 4 can be written as a fraction as 4/1. On the other hand, not all numbers are perfect squares, like the square root of 17. If you punch that in your calculator, you're going to get 4.01 something, 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 and it will go on forever and ever and ever with no repeating pattern. So the only way to get an irrational number, one that cannot be written as a fraction, is a never-ending and non-repeating decimal. Here is a further example of irrational numbers. Irrational numbers can only be written as decimals that do not terminate or repeat. If a whole number is not a perfect square, then its square root is an irrational number. So for example, when I plug the square root. When I plug the square root of 2 into my calculator, it tells me this line of numbers. Notice that there is no repeating pattern and that there is no end in sight. Now that being said, eventually the number stopped, and the reason it stopped is because my calculator screen was only so big. If the last number is rounded, that's called rounding. If, on the other hand, let's say my screen ended right here at the 5, and the 5 wasn't rounded, that's called truncating. So if this is my calculator, and only the digits in this little rectangle, here are my keys, and only these digits are showing, that's called truncating. So truncating, cutting off the numbers without rounding. And rounding is following rounding rules. These are the two ways that calculators handle irrational numbers. So if it were rounded, this same screen would be 1.414213, but this 5 would be a 6 because the 6 says to round up. Just know or be aware that you can never really count on that last number actually being what it says. That's the main point of that. I think I put this in your notes to try to help you understand the difference between truncating and rounding. A repeating decimal may not always appear repeating on a calculator because some calculators show only a finite number of digits. So if you typed 125 divided by 30 into your calculator, it would look like this. This makes it seem like it's not a repeating decimal. However, this calculator rounded the last digit and made the 6 a 7. So, the calculator expression does not guarantee that the 6 is repeated, but the possibility should be anticipated, and know that this is actually a rational number because it's a repeating decimal. You can also see it's rational because, right here, this is a fraction. And all fractions are rational. Uh-oh, we got one that didn't show up. All right, rational or irrational? Be prepared to defend your form by naming the fraction form. 432 8/10. Rational or irrational? So what you should be thinking in your head is fraction form or no fraction form. That's the debate. In this case, we know it's rational. It's rational because 432 8/10 can be written like this as a mixed number. So it's rational. The next one. The 0.1212, well, that one is also rational. It's rational because we have a repeating decimal. An irrational number is never ending, like this, but also non-repeating, and this one is repeating. And repeating decimals can be written as a fraction. And in this case, I'll teach you how to do this, but it's 12/99. The next one, 0.120120012, and it goes on forever. Notice that this is not a consistent repeating pattern. This is irrational because there is no fraction form, or because it's never ending and non-repeating both. Okay, and the last one is 15. 15, can you write that as a fraction? I think we can. So this is rational. And let's write it as a fraction, 15 over 1. Okay. I'm trying to look quickly for what this missing number is. All right. Oh, 3/4. 3/4. Is that rational or irrational? Rational numbers can be written as fractions. It's already a fraction, so I know it's rational. All right, so if it has a fraction form, it's rational. If it doesn't, it's irrational. Let's try this. Here is a set of all of the real numbers in the world. It's kind of like if you were in science, this would be all the animals, here would be all the vertebrates, here would be all the invertebrates. In math, we have all of the real numbers. Any number that could be on a number line. We have rational numbers, meaning they have a fraction form. And we have irrational numbers that don't. All right, so notice that you have your integers, which is positive and negative whole numbers. And this could be -2 over 1. This could be -3 over 1. You've got your whole numbers, 0, which is the same as 0 over 1. Natural numbers are your counting numbers. 1 is the same as 1 over 1. 2 is the same as 2 over 1. 3 is the same as 3 over 1. 27/4 is already a fraction form. 4.5 is the same as 4 and 5/10. The square root of 4, what number times itself, I'm working on this one, what number times itself gives me 4? 2, which is the same as 2 over 1. Okay? Let's try some of these out. Write all of the names that apply. 3/5. 3/5 is rational. It falls into this category here because it's a fraction form. It's not an integer because integers are negative and whole, positive whole numbers. It's not a whole number because it's a fraction, and it's not a natural number or a counting number. So this is a ratio or a fraction, and so all numbers that can be written as a fraction are rational. What about this one? -12 and 75/100. Does it have a fraction form? Sure does. -12 and 75 over 100. You don't even have to reduce it. You can and call it -12 and 3/4. So you would say rational. The square root of 5. The square root of 5. Is there a number that when you multiply it by itself, not multiply by 2, but multiply by itself, that gives you 5? No, there isn't. It cannot be simplified or written as a ratio, and so this is an irrational number. That falls in this category on the right. Okay, what about this? Oops, did I get the same one in there twice? I think I did. Sorry about that. How about this one? This one could be tricky. We actually have to simplify this one first. Think to yourself, what number times itself gives me 16? That answer is 4. So the square root of 16 is 4. 4 over 4 is equal to 1. Well, that's a fraction, isn't it? It's also, let's classify the number 1. First of all, it's rational. I could write it as 1 over 1. It's a positive or negative whole number, so it's an integer, it's a natural number, and it's a whole number. It's everything. It's all of them. The main point of today's lesson is to know that it's a rational number. Everything else is just a review from previous years. And that part will not be on your test. Just rational or irrational. So write the following numbers in the diagram, or say rational or irrational. I'd like you to pause the video and do these 8 problems. Then come on back and compare what you got to what I got. All right, for the first one, you should have gotten rational because 12 over 1. The second one is rational, negative 35 and 9/10. Notice I didn't, when I converted this to 9/10, I didn't even, or you don't have to worry about simplifying these, although that one can't be simplified. Number 3, the square root of 21. Is there a number such that when I multiply it by itself, it equals 21? Nope. So that one falls in the irrational category. If I punch this into a calculator, I get a long, never-ending, non-repeating decimal. And then number 4, it's rational because it equals 0. Okay, the square root of 4. What number times itself equals 4? Well, that's rational because your answer is 2, which is the same as 2 over 1. Number 6, the square root of 50. Now this one throws people. There is not a number that when you multiply it by itself gives you 50. 25 times 2 is not 25 times 25. That's something different. Don't confuse it with adding. So this one is irrational. It leaves you with a never-ending and non-repeating decimal. When you punch it in a calculator. Then there's pi. Pi is also irrational because it makes a never-ending, non-repeating decimal. This last one is the trickiest. Everybody remembers pi as being 3.14. And I am telling you, put a star by this one and write watch out. Because this is an approximation of pi. This one is not actually pi. Pi continues on forever and ever. 3.14 ends, it terminates. And you could write this as 3 14/100. So this one is a rational number. You have a decimal version. So make sure you're careful with this one. That is not equal to pi. It's approximately or close to pi. All right, next let's talk about how to evaluate. Evaluate by plugging the numbers in. Remember that if you plug in a negative number, use parentheses. I'm going to let you pause the video and work these couple problems and come on back to compare your answers to mine. All right, I plug in a number into your equation and I get 1 over negative 3, which is the same as negative 1/3. That's rational because it's a fraction form. The next one, 7 minus negative 5 all over 3 times 6. Remember, minus a negative is the same as adding the opposite. So I get 12 over 18, and I'm supposed to write it in simplest form, which means reduce it. What is 12 and 18 both divisible by? 4. Nope, not 4. Not 4 at all. How about 3? And I get 4. I can't even think today. 4/6, but I'm not done yet. There's a bigger number. We could have divided by 6. Sorry about that. And I get 2/3. The last one, letter C. Let's see. 6 plus 9 all over negative 5. That equals 15 all over negative 5. When I reduce that, I get negative 3. Okay. Try evaluating this one when x equals 6 and y equals 2. Pause the video, work the problem, also work these two where they're getting more involved, and then come on back and compare your answers to mine. All right, so I substituted the numbers in, and now I'm solving using the order of operations. Inside the parentheses, you use order of operations. 27 minus 8, I get 19. 3 times 19 all over 60. 3 times 19 is, 3 times 10 is 30. 3 times 9 is 27, so 57. And then I should be able to reduce these. So 57 divided by 3. So if I divide the numerator and the denominator by 3, I get 19/20. I used my divisibility rules. For those of you who weren't sure how I knew that was divisible by 3, I took 5 plus 7 and got 12. And I saw that 6 plus 0 is 6, and I knew both of those sums were divisible by 3. And that's how I found that 19/20. All right, here I've got x is -2. Make sure you put parentheses around that -2 when you substitute it into the equation. -2 minus 5, that's the same as -2 plus -5, and I get -7 all over -21. I can simplify that by dividing the numerator and the denominator by -7 over -7. Because they're negative on the top and the bottom. So I get 1 over 3. All right? Let's try one more. Let's see. 6, oops. When I'm simplifying this, I replace the 6 and the n, and I get -6/7, or you could leave it like this too. Okay, and then the last one. 6 over 6 squared plus 4. Now, I need to reduce the denominator. 6 squared is 36 plus 4. 36 plus 4 is 40. Then when I divide those both by 2, I get 3/20. My answer is 3/20. All right, so your homework today is going to be the 4-6 worksheet. So give that a try. A lot of it is most like, not as much classifying, but more solving and evaluating. You will need to show work and how you substituted numbers into those equations. So do your work on a separate sheet of paper and attach that to the Google Classroom